Isang magandang araw sa inyong lahat. Sa videong ito ay magsosolve tayo ng isang sample problem patungkol sa Uniform State Uniform Flow Systems or USUF systems. So babasahin ko muna yung problem para sa inyo. An insulated 2 cubic meter rigid tank is to be charged with R134A from a line flowing the refrigerant at 3 megapascals and 90 degrees Celsius. The tank is initially evacuated and the valve is closed when the pressure inside the tank reaches 3 megapascals. Find the mass in the tank and find its final temperature. So according to our word problem, the volume of this tank that you can see over here is equal to 2 cubic meters. So it is a rigid tank, so ibig sabihin hindi nagbabago yung iyong volume. Also, we are using R134A, so make sure na mamaya sa ating thermodynamic tables ay nandun tayo sa R134A tables. It is also mentioned na yung pressure ng ating refrigerant na nagfo-flow ay 3 megapascals, or in other words, we have 3,000 kilopascals. We are going to write it in kilopascals dahil yung ating thermotables ay naka-express in terms of kilopascals. TI is basically 90 degrees Celsius. So, bakit ko sinabing TI at PI? It's because of the fact that this fluid line is entering your system. So, in our energy equation, yan yung mga may subscript na I. According to our problem, the tank is initially evacuated. This means na sa simula ng ating process, the mass inside the system is just equal to 0 kilograms. It is initially evacuated, ibig sabihin wala siyang laman sa simula. The valve is closed when the pressure inside the tank reaches 3 megapascals, and this clause actually means that the final pressure of your system is actually 3 megapascals, or in other words, P2 is equal to 3,000 kilopascals. In this problem, ang pinapahanap sa atin na yung mass ng refrigerant inside the tank after the process, so we have M2. Also, the final temperature, T2. So, let us solve this problem. Tulad na lang ng ibang word problems na sinasagutan natin, magsimula tayo sa pag-derive ng ating first law equations using the energy balance and mass balance. What you can see here are the two different forms of our first law equations for USUF systems. Itong first set of equation na ito, tawagin nating set A, ay actually yung first law for USUF in time rate form. So kapag sinabi nating time rate form, yung mga masses ay naka-express in terms of mass flow rates. In this case, you have m.I and m.E. And the unit is in kilograms per second if we are using SI units. Also, it has a derivative dECV over dt. We also have the time rate forms of the heat and the work transferred Q dot and W dot CV respectively. In this set of equation, tawagin nating set B. Ito naman yung set of equation na hindi naka-time rate form. Ibig sabihin, heat is just Q that has a unit of kilojoules when you are using SI units. MI and ME are in kilograms and they are not in kilograms per second dahil hindi nga sila naka-time rate form. So now, what is the difference between these two? Actually, set B can be derived from set A over here. So you can just multiply both sides of this equation by dt and then take the integral of both sides. So over here, makikita ninyo na meron tayong delta ECV as the integral of dECV. At makikita ninyo sa ating set B equations na wala na yung time derivative na nandito. So these dots will vanish. Same goes with the mass balance equation. You multiply both sides by dt and then take the integral of both sides, which is why you have delta mCV is equal to the summation of mi minus summation of me. And again, you can notice na nawala lang yung dot dito. Now that we know that they are practically the same, alin dito sa dalawa ang gagamitin natin for this word problem? If we inspect the given, wala namang time na binigay, no? At yung ating mass ay naka-standard form, hindi siya naka-time rate form, which means that we focus on the set B equations. So let us further simplify the first law equation for the uniform state, uniform flow system based on the word problem that we have. According to our problem, we have an insulated tank, which means that the heat transfer Q is just equal to 0. Remember, by definition, kapag sinabi nating insulated system, walang heat na nagta-transfer in and out of the system. Also, according to our problem, we are using a rigid tank, which means that boundary work is just equal to 0. Now, since boundary work is 0 and wala namang ibang types of work na associated with the system, wala namang electrical work or whatsoever work that is being added or being released by the system, we can just say that WCV is just equal to 0. Also, according to our schematic diagram over here, we only have one stream of mass flow that is going into the system. So we can just omit the sigma notation over here. Also, wala namang given na velocities and elevations yung ating streams of mass flows, which means that we can just neglect the effect of your kinetic energy and your potential energy. Going back to our schematic diagram, makikita natin na walang mass na nagpa-flow out of the system, which means that this value over here is just equal to 0 and practically drops the effect of this entire expression. So this entire expression will just vanish. Which means na ang ating energy equation ay delta ECV is equal to MI HI. So as you can see from a really complicated equation, we were able to narrow it down to this. Now, if you can recall in the previous lecture, delta ECV can also be expressed as ECV2, meaning you have the final total energy of the control volume minus ECV1, which is the initial energy of your control volume. And you also know that ECV2 and ECV1 are expressed as this and this respectively. Fortunately for us, alam natin na yung ating tank ay initially evacuated, which means that MCV1 is just equal to 0. Basically, this expression has no effect in our final equation. So we can just say that ECV1 is just equal to 0. Now, how do we simplify ECV2? Pwede nating i-assume na yung ating system ay fixed lang with respect to an inertial frame of reference, which means that the effect of your kinetic and your potential energy components are negligible. In the end, we can say that ECV2 is just equal to MCV2, or basically M2, multiplied by U2. Therefore, delta ECV according to this set of equations is just equal to M2 multiplied by U2. Now, take note that we have two expressions for delta ECV, which means that we can further combine these two, giving us MIHI is equal to M2 U2. So, take note na this delta ECV is just equal to this delta ECV over here, so we just equate these two. This is our resulting equation from the energy balance equation. Now, let us proceed with our mass balance equation. Following the argument na isa lang yung mass na nagpo-flow papunta sa ating system, we can just omit this sigma notation over here and say that this expression, summation of ME, is just equal to 0. Therefore, we can say that M2 minus M1, which is your delta MCV, is just equal to MI. We know that M1 is just equal to 0, and therefore we have M2 is equal to MI. Combining this equation with the one that we derived a while ago, so yung resulta ng ating mass balance equation at ng ating energy equation, pagsasamahin lang natin. So we have M2HI is equal to M2 U2. Dividing both sides by M2, we finally have HI is equal to U2. And this is the final governing equation of this system. Imagine mula sa dalawang equations na komplikado, dahil sa iba't ibang conditions and assumptions ng ating system, na-derive natin ang napakasimpleng equation na ito. So this equation will guide us in solving this particular problem. So yung next part ng ating solution ay magi-involve ng pag-define ng iba't ibang states sa ating system. Fortunately for us, we only have two states. We have state I and state 2. So first, let us define state I. Alam natin na ang initial pressure ng ating system ay 3,000 kilopascals. At ang ating initial temperature, Ti, is equal to 90 degrees Celsius. Let us consult our thermodynamic table. So, take note na ang ating working fluid ay R134A, which means na dapat sa ating thermodynamic tables ay nandun tayo sa R134A. In the reference book that I am using, which is Fundamentals of Thermodynamics, andito tayo sa table B5. So we have a temperature of 90 degrees Celsius and that temperature is over here. At makikita natin na sa temperature na 90 degrees Celsius, ang kanyang saturation pressure ay 3,244.5 kilopascals. This saturation pressure is definitely larger than our actual pressure, which is 3,000 kilopascals, which means that our working fluid is superheated vapor. So let us just put that on record. The saturation pressure at 90 degrees Celsius is 3,244.5 kilopascals. And this saturation pressure is larger than your actual pressure PI. That is just equal to 3,000 kilopascal. Again, kapag ang ating saturation pressure ay mas malaki sa ating actual pressure, we have superheated vapor. Or in other words, kapag yung ating actual pressure ay mas maliit sa ating saturation pressure, we have superheated vapor. Which means that we have to consult our superheated tables. Puntahan natin ang pressure na 3,000 kilopascals and it is somewhere here. At makikita natin na at 90 degrees Celsius, ang kanyang enthalpy ay 436.19. So you might be wondering kung bakit enthalpy ang ating hinahanap. If you can recall in our energy equation a while ago, we derived HI is equal to U2. So the relevant property for our inlet state, which is state I, is our enthalpy. Let us write down the value of this enthalpy. And from our energy equation and mass balance equation, again, we have HI is equal to U2. Which means that the value of U2 is equal to 436.19 kilojoules per kilogram as well. So this value will help us on fully defining state 2. So let's proceed with our second state. Meron tayong state 2. At alam natin na yung ating pressure at state 2 is just equal to 3,000 kilopascals. Also, our internal energy U2, based on our derivation a while ago, it's just equal to 436.19 kilojoules per kilogram. Let us consult our thermodynamic tables. So, since andito na tayo sa ating superheated tables, samantalahin na natin, no? Makikita ninyo, sabi dito, we have SAT. Masasabi natin na yung saturated vapor internal energy, or basically UG, is just equal to 411.83 kilojoules per kilogram. So how does that compare to our actual internal energy? Let me just write that down. And we can say that the actual value for U at state 2 is actually larger than the saturated value at the pressure of 3,000 kilopascals. This means na ang ating refrigerant R134A ay superheated vapor. Ano ang pakinabang nito sa atin? Ibig sabihin yung tables na ating i-inspect ay dun pa rin sa superheated tables. At 3,000 kilopascals, the value of our internal energy is 436.19 at makikita natin na ang 436.19 ay nasa pagitan nitong dalawang values na ito. Which means that the temperature of our refrigerant, which is one of the unknowns, is actually between 100 degrees Celsius and 110 degrees Celsius. Now, we can just perform linear interpolation in order to solve this problem. Let us just write down the values of interest for U and their corresponding temperature values. We have our internal energies in kilojoules per kilogram, and we have our temperatures in degrees Celsius. So, kopyahin ko lang yung values na ito from our thermodynamic tables. We have the lower bound of our internal energy, which is just 433.77 kilojoules per kilogram, and the corresponding temperature is 100 degrees Celsius. The upper bound, on the other hand, is equal to 446.48, and its corresponding temperature is 110 degrees Celsius. Ang value ng ating internal energy at state 2 ay equal lang sa 436.18 kilojoules per kilogram. So, take note na ang actual value ng ating internal energy ay nasa pagitan lang ng dalawang values of interest na ating isinulat. So, we are looking for the final temperature, and this can be solved using linear interpolation. Paano mag-perform ng linear interpolation? Let's press menu, and then go to statistics, and select y is equal to a plus bx. Bakit natin pipiliin itong form na ito? Because we are going to perform linear interpolation. I-input lang natin yung values ng internal energy at the x column, and then later we input the corresponding temperature values at the y column. Press AC. Don't worry, yung values na in-input natin ay nakastore lang sa ating data. And then input the actual value for internal energy, which is just 436.19. Press Option. Go down and then select regression. And then finally select y hat over here. Now, why are we selecting y hat? Basically, what we are doing here is that we are finding the corresponding y value, which in this case is the temperature dun sa table na in-input natin kanina, for an x value of 436.19. Whereas the x values in our calculator a while ago dun sa table na in-input natin ay yung mga internal energies. Literally, we are solving for the corresponding temperature value for an internal energy value of 436.19. If we press equal, we have 101.9040, which is the final temperature in our system. Let me just write that down. Finally, we have T2, or basically T final, is equal to 101.9 degrees Celsius. So this is one of the unknowns that we are looking for. Isa pa sa mga pinapahanap sa ating problem ay yung final mass ng ating system. This can actually be solved by recalling the equation V2 multiplied by the specific volume, small letter v2. Pwede nating isolve ang specific volume at state 2 using our thermodynamic tables and linear interpolation. Balikan lang natin ang thermodynamic tables natin kanina. For an internal energy of 433.77, we have the corresponding value for specific volume that is equal to 0.00665. And for 446.48, the corresponding specific volume is equal to 0.0734. We can actually add these values of specific volume in the table that we have constructed a while ago. So, isulat lang natin ang corresponding values ng specific volume na naka-express in terms of cubic meters per kilogram. There we go. So, for this part of the problem, kailangan nating baguhin ng kaunti yung data na nakastore sa ating calculator. To do that, just press Option and then select Data. So, basically, pindutin natin yung 4. And then, replace the corresponding y values para hindi na kayo magta-type ulit, no? So, palitan na lang natin yung values ni y. So, instead of temperatures, we have the specific volumes. There you go. So, applying the process that we did a while ago, press AC, and then input 436.19. Press Option, go to Regression, and then finally select y hat. Pressing equals, we have 6.7814 times 10 to the negative 3 cubic meters per kilogram. Let me just write that down. Now, take note that we are looking for M2. So, dividing both sides of this equation by the specific volume, we have M2 is equal to capital V2 over small v2. At alam naman natin na ang ating final volume ay equal lang sa 2 cubic meters. At alam natin na ang specific volume ay equal lang sa 6.7814 times 10 to the negative 3 cubic meters per kilogram. The cubic meters will cancel out, and we have M2 is equal to the quotient of these values. So, plug in lang natin sa ating calculator. Finally, we have a mass of 294.9244. So, these are our final answers. Ang ating system ay may final temperature na 101.9 degrees Celsius at ang mass ng refrigerant na pumasok sa loob ng ating system ay equal lang sa around 295 kilograms. This is the entirety of our solution at kung makikita ninyo mula sa ating napaka-komplikadong energy and mass balance equations, nakapag-derive tayo ng napakasimpleng governing equation na siyang tumulong sa atin para ma-solve ang problem na ito. Thank you for watching this video. I hope you learned something and see you in the next videos.